Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, Indira Gandhi National Open University, and today I'll be discussing with you about asymptotic notations of algorithmic complexity. So the very first question I would like to answer is, what is asymptotic notation? Well, the asymptotic behavior of a complexity function fn refers to the growth of function fn as n gets very large. It estimates how slow the program time complexity will grow for large inputs. So the idea is, as n is moving or n is increasing, what is going to be timing requirements of a particular function. Now the timing requirements are always determined in terms of the size of the problem. So if I consider two complexities or two solutions whose complexities are given and they are solutions to the same problem of the size n, then how we can compare these two solutions? For example, if first solution to the problem is where T1n is 1000 n square and T2n is 5 n to the power 4. Which of the two algorithm is better as far as asymptotic notation is concerned? Well, the fact goes that T1n is going to be greater than T2n, that is, the time taken by algorithm 1 is going to be more than algorithm 2, provided n is less than equals to 14. Okay. However, as soon as n becomes more than 14, that is, it becomes 15 or more, then the first algorithm, right, T1n is going to be less than T2n, even though it has a constant value 1000. So 1000 n square is going to be less than 5 n to the power 4 for any value after 14, that is 15 and onwards. So which algorithm we will be preferring? Definitely we will be preferring the first algorithm. So that is the basic essence of asymptotic time complexity, where we are trying to predict which algorithm is better as n is moving towards a very large value. Now, what way we can define this asymptotic notation? There are three basic notations, and let us define them one by one. The very first notation is called big O notation. It is represented with the help of O, and it represents the upper bound or a worst case of an algorithm, which finds the maximum number of steps to solve a problem. Now, why we are interested in upper bounds? Because it bounds the growth of the running time from above for large values of input size. So we know from the top that this particular algorithm is not going to grow beyond this particular point. It notifies that a particular procedure will never go beyond a specific time for every input n, and advantage of big O notation is it makes algorithm much easier to analyze, since we are conveniently ignoring the lower order terms. So we are just interested in the higher order terms. How it is defined? Well, let fn and gn be two positive functions, each from set of natural number, okay, to the positive real number, which is going to be the range. Then fn is defined to be of order gn if there exists two positive constant c and n0 such that fn is less than equals to cgn for all n greater than equals to n0. Now that definition looks very complex, but look into the graph. It clearly defines that CGN is more, right, greater than equals to Fn, right. So what we really need to know, we need to know the value of C as well as value of N0. Now you can clearly see in the graph below N0 the value of Fn may be larger in certain cases, but after N0 in no case the value of Fn is going to be greater from Cgn. So Cgn is going to be more after the cut point which is N0. So this is how the big O notation is defined. Let us take an example of big O notation. So if I want to determine the complexity of function Fn, which is represented as 3n square plus 4n plus 2, what I need to know? I need to determine two values, C and N0, right. So let us assume, since the topmost term or the topmost polynomial term here is n square. So let us take Gn as n square, okay. And what I want to determine is Fn is less than Cgn for all n greater than N0, all right. So that is what we have written at the next step, that is 3n square plus 4n plus 2 has to be less than equals to Cgn for all n greater than N0. Now the next thing which let's assume is let's take the value of N0 to be 1. Then what is going to happen? It will convert to 3 plus 4 plus 2 should be less than equals to C for all n greater than equals to 1, right. So any value of C from 9 or above, right, in this particular case you are going or you are assured of that this particular function, okay, Fn, okay, this particular function is going to be less than 9 n square all the time, right, and that is where the complexity is. So the order or the big O complexity of function Fn is going to be of order n square, because C and N0 are not counted towards the order, they are used to prove the order, that is all. Now another interesting example is, can n cube is order n square? Can we say that? Well, you need to find C and N0 so that Fn equals to n cube is less than equals to Cn square for all n greater than equals to N0. Now what does it require? That n should be less than equals to C for all the values of n greater than equals to N0. Now these two are contradictory statements, so this is not possible. Therefore n cube cannot be represented by order n square. N cube will be represented by order n cube only. Now let us move to the second representation or second notation, which is called big omega notation. Now the big O notation was describing the upper bound, whereas the big omega notation describes the asymptotic lower bound of an algorithm, whereas big O notation represents an upper bound. Generally we say that an algorithm takes at least this amount of time without mentioning the upper bound. So that is where big omega notation comes into picture. How do we define that big omega notation? Well, once again let Fn and Gn be two positive functions, each from the set of natural numbers domains to positive real numbers, which is the range. Then Fn equals to omega Gn if there exists two positive constants, capital C and N0, such that Fn is greater than equals to, in the case of big O it was less than equals to, now it is greater than equals to Cgn for all values of n greater than N0. Now look into the graph, it clearly defines. Now you can look into the location of Fn. Fn is now at the top and Cgn is the line which is at the bottom, and beyond n0 Cgn or Fn exceeds Cgn, right. So, that is what is the basic definition for this particular big omega notation, which defines the lower bound. Now, the same function, right. So, what is going to be the big omega definition as far as if the function Fn equals to 3n square plus 4n plus 2. Now, in this particular case, since we are saying Fn is greater than equals to Cgn, what we can really do, we can simply ignore the terms like 4n plus 2. Okay, we do not require to actually use 4n plus 2 for evaluation, right. So, we actually can simply say that the value of C, right, or should be less than equals to 3. Right. So, if the value for the value of C less than equals to 3 for all values of n greater than 1, you are going to get this Fn greater than equals to Cgn. That means once again the omega or the omega complexity, if we are defining the omega complexity, the lower bound of this function is also going to be of omega n square only, right. So, this it is once again big O as well as big omega, both for this particular function are of the order n square only. Okay. Now, the last but not the least is big theta notation, which basically represents the tide bounds. Now, big theta function notation basically says that function Fn equals to theta Gn if the value of Fn lies between C1 Gn and C2 G2. So, lower bound and the upper bound for a sufficiently large value of n. So, it is basically a mixture of basically at the lower bound you have theta, at the upper bound you have big O, and in between basically the tide bound is represented with the help of big theta. So, let Fn and Gn be two positive functions each from the set of natural numbers, which happens to be the domain of that, and to the real to the positive real number, which happens to be the range, then Fn equals to theta Gn, right. If there exists positive real number C1 and C2 and n0 such that 0 is less than equals to C1 Gn, which is less than Fn, which is once again less than C2 Gn for all values of n greater than equals to n0. And what again, once again you can see the graph, the value of Fn is in between the C2 Gn, okay, and in the second case it is C2 Gn. So, it is between, it is sandwiched between the two. C2 Gn basically represents the upper bound and C1 Gn is representing the lower bound, and in between basically this is what basically the in between is the function value. So, this is how big theta notation is represented. There is a typical theorem of big theta which says for any two functions fx and gx, fx equals to theta gx if and only if fx equals to order gx and fx equals to omega gx. So, if Fn is theta Gn, this means that the growth of Fn is asymptotically at the same rate as that of Gn, or the growth of function n is also is not asymptotically slower or faster than the function Gn. So, no matter what the value of n is. So, this is the way we define these three terms. Now, if I want to find big O, big omega and big theta for a particular function, okay. So, if I want to find it out for Fn equals to 5n cube plus 6n square plus 1. Now, here the degree of polynomial is 3, okay, because the highest term is 5n cube and all terms are positive. Therefore, value of 5 is greater than equals to C1, okay. So, we have a lower bound, okay, as well as 12 is less than equals to C2. So, it is more than C1 n square, that is 5 n square, but it is going to be less than 12 n square for all values of n0 which are greater than equals to 1. Therefore, for this particular function n, the upper bound is going to be order n cube, lower bound is going to be omega n cube, and Fn also is basically represented by theta n cube. So, this is how, because order as well as omega, or that is O and omega, both are in terms of n cube, therefore, theta is also going to be the n cube only. So, for the function where upper as well as lower bound both exist, then you can define it to be in terms of big theta. Now, what are the drawbacks of this asymptotic analysis? Well, consider the time complexity of worst case of two solutions to a problem of input size n, the same one which we have used earlier, where T1 n was 1000 n square and T2 n was 5 n square in this particular case. Now, both of these algorithms are asymptotically the same. These are slightly different from the earlier one, right? Asymptotically same, why? Because n, as n is moving towards infinity, we will be calling it of order n square, right? So, asymptotically we are defining both the algorithms to be n square, and we will be forgetting these constants 1000 and 5, right? Since we ignore the constant in asymptotic analysis, it is difficult to judge which one is more suitable under what circumstances. So, this is a typical problem when the constant value is different, one is small and one is very large, yet the polynomial term is same, like it's in both the cases you have n square. Then since you are using the asymptotic notation, you won't be able to judge which of the algorithm should be used, because those constants are simply ignored. Now, another situation is worst case versus average performance, right. So, if an algorithm A has better worst case performance than algorithm B, but the average performance of algorithm B is better than algorithm A, then algorithm B is a better choice than algorithm A, whereas we might be considering the worst case scenario if we are doing the asymptotic analysis, if we are finding out the upper bound in a particular situation. So, therefore, we need to be really careful at times that what kind of asymptotic analysis we are using for what particular purpose. Now, once we know about this asymptotic analysis, let us try to understand some common running time which are used when we are defining complexity of algorithms. Now, some of these common running times, let us start with order n, which is also called the linear time complexity. Now, linear time complexity is basically defined if the time complexity is at most a constant factor time the size of the input, then it is known as linear time complexity. It is represented as Tn is less than equals to k and n, k into n, or Tn equals to order n. Okay, this is the mathematical representation for order n, where the function Tn function is Tn, where n is the input size and k is the constant. An algorithm of this type of complexity generally completes the execution in a single pass. Let us take a simple example of order n. Suppose you want to search for minimum value in an array of size n. So, how will you proceed? You will first assign the minimum value, let us say minimum equals to a1. So, the first value is assigned to variable minimum, and thereafter we will do the iteration for I equals to 2 to n. If ai is less than minimum, change it with the minimum value, and if this particular and this is the end of the algorithm in a sense. So, what you are doing is you are repeatedly checking, right. So, those checking and sometimes you are interchanging, right. However, this particular algorithm, that is, if we say that checking is taking or even if we are saying it is the interchange, every time the interchange is taking place, the worst case behavior is there, it is going to, the algorithm is going to be completed in the n iteration only, right. It is in the one basically single pass of execution, right. So, therefore, the complexity of this algorithm happens to be of order n. Now, another important point or another important time complexity is logarithmic time. Well, it is written as order log of n. If the time complexity of an algorithm is proportional to the logarithm of the input size, then it is known as order log n time. For example, the running time of a binary search algorithm is order log n. How does it work? The log n algorithm works or log n time complexity work. For example, in binary search, suppose you have 100 elements. What will you do? You will compare with the middle value only, right. So, then you are dividing the complete search space into 2. So, the value is going to be less than the important requirement for binary search is that all the numbers should be ordered in some sorted order. Let us say if they are increasing or decreasing, it does not matter, but on that basis when you compare with the middle value, you take a decision, I have to go on search in the left subset or the right subset. So, by comparing at the middle value, you have divided the problem into half. Then you will be comparing with the middle of the whatever is the next comparison is going to be, where you are supposed to search in that subset only, and the other subset you will be just ignoring. So, every time you are dividing your problem by half, right, that is where the log n time complexity comes into picture, because here we are talking about log 2 basically in this particular case. All right. Then comes order n log n. It is a very common running time for many different algorithms which are solved using divide and conquer technique. Now, divide and conquer technique is once again the binary search is also divide and conquer technique. However, binary search has a log n situation only, and in merge sort, since you are doing other operations also, so n log n is the common running time, and n log n is for is there for quick sort, it is there for merge sort. Average time behavior of quick sort algorithm is also n log n. Okay. So, the common operations among all these problems are in the splitting of array into equal size subarray and then solving the problem into smaller arrays. However, in merge sort, you are once again combining the data, so that takes n time, and therefore, dividing the problem into half and half and half and so on recursively, it basically refers to log n time complexity. So, n for doing other operation, log n for division. So, this particular logarithmic time complexity works that way. Then comes the quadratic time complexity. Well, quadratic time complexity basically refers to as order of n square. It occurs when algorithm has a pair of nested loops. The outer loop iterates, let us say, order n times. For each iteration, the inner loop iterates, takes order n times. So, order becomes order n square. The worst case time complexity for algorithms like bubble sort, selection sort and insertion sort. Okay. So, these are of the order n square. Next is the polynomial time. Now, the polynomial time algorithm is basically is obtained when a search over all subsets of a size k is performed. So, you divide it into a number of subsets. Earlier you were dividing it into 2, now you are dividing it into number of subsets and you are searching on all these subsets. So, first find the distinct subsets of size k of n elements of a set, take a combination of k elements at a time then. And a very simple example in this particular case is the problem to find an independent set of nodes in a graph. Now, what are these independent sets, independent nodes? Well, a set of nodes, okay, is in which no pair of nodes have an edge between them. That is called an independent pair of nodes, because these nodes are not connected to each other. However, they may be connected through other nodes, that is all right, but among between themselves they do not have any edge. Okay. So, this problem can be formulated as, given a constant k and a graph G having n nodes or vertices, find an independent set of vertices of size k. And if you take a brute force method to solve this problem, it would require searching all subsets of k nodes. For each subset, it will examine whether there is an edge connecting any two nodes for each subset S of size k, thus leading to order n to the power k or the polynomial time. Next is the exponential time. Now, exponential time is basically a situation in which it is actually beyond the polynomial time complexity, and there are two types of these bounds normally. One is called exponential time, which is order 2 to the power n, and another is called factorial time, which is order n factorial. Example for this is to find the independent set of graph G of a maximum value instead of some constant k. In the earlier case, we were finding it for k. Now, we have to find it for some some maximum value. So, you will start from 1, then 2, then 3, like that. Okay. So, we start from not 1, we start from 2. This problem can be formulated as, given a graph G having n nodes vertices, find a maximal independent set of nodes. So, these are some of the run time. So, how they relate to each other, right? Which algorithm is better? So, if a constant time algorithm irrespective of the size of n, this particular algorithm is going to take just constant time, right? It is less than, this is the best algorithmic time which can happen, but no algorithm would have such a such kind of time. Okay. It is less than order log n, which is called logarithmic time. This is less than order n, which happens to be called linear time. It is less than order n log n, okay, which is once again less than order n square, which is quadratic, which is less than order n cube, which is called cubic, which is less than order n to the power k, which is called polynomial, and these all are less than order 2 to the power n, which is called exponential time complexity. The slower is the asymptotic growth rate, the better the algorithm is. So, we want to develop algorithm in the linear time, logarithmic time, or n log n or quadratic time, right? That is our normal situation. And the example of situations where this can be seen is the merge sort algorithm is better than bubble sort algorithm, because the complexity of merge sort algorithm is n log n, whereas bubble sort has the complexity of n square. A binary search algorithm is better than a linear search algorithm, because the binary search algorithm has a complexity of log n, order log n, whereas linear search has a complexity of order n, that is linear. So, with this we would like to end this particular session. So, in this session we have discussed about the asymptotic complexity of various notations, which happens to be big O, the upper bound big omega, the lower bound and big theta, the tight bounds, and in addition we have explained some common running time of algorithms with the help of examples. Thanks for being with us. Bye for now.